Hi, this is Fabian from Google's security research team. I'm talking about a new open source test tool that was developed as part of our OpenSK initiative to bring open source to security keys. As a software engineer, I am working on two open source projects. One is OpenSK, our open source security key framework for FIDO2. I'll briefly introduce you to it later. At the same time, I worked on testing, and today I want to announce the launch of the resulting tool. We realized during development of a security key that getting the details right is hard. Here's one example. There are two relevant specifications: WebAuthn for communication between website and browser, and CTAP2 for communication between browser and security key. Those are tightly coupled and often share the same data structures, but sometimes they differ in details. In such cases, even major brands of security key vendors have different implementations. Our goal is to increase security key adoption, so we want to make behavior more consistent. In the specifications, websites are often called relying parties. We want security keys to be something that relying parties can rely on. Therefore, we are publishing our CTAP2 test tool to promote open testing for a consistent user experience. Also, we share test results of all tested devices to make it easier for users and websites to trust security keys. So why would you use the test tool? If you are a security key vendor, this tool is a resource during development. As a user, you can check out which security keys support the features you care about. And if you host a website, we want to make it easy for you to trust more security keys as a first or second factor. In this talk, I want to give you an overview of our new test tool. Then I'll briefly introduce OpenSK before demonstrating the test tool live. Last, I'll show you how you can contribute test results. Let's start with an overview of the test tool. First of all, it's free. Its source code and all test results are available on GitHub. It runs with a single command in your terminal. We shared the first version and its results with vendors earlier. Discussions with vendors already impacted the ecosystem, including fixes in tested security keys, the CTAP specification itself, and our test tool. We are happy to see implementations and the underlying protocol converging. One disclaimer: this is not an official FIDO Alliance product. We are closely working together, but if you're interested in certification, please make sure to check out their website. Also, we recently added experimental fuzzing functionality. Now some technical details. We are testing version 2.0 of the CTAP2 specification. When version 2.1 is out, we will automatically detect what the security key supports and adapt the tests accordingly. We wanted to make the test tool as easy to use as possible. You don't need any configuration. The same goes for available options. Depending on the device's features and extensions, read your device information and personalize the test for you. For transports, only USB is supported at the moment. One thing I want to emphasize is that the test tool inspects all parameters in all responses, so security keys stay close to the specification. We want to make sure that all brands work with all browsers and users don't run into compatibility issues. This shows where our tool differs from the FIDO Alliance conformance tests. While we don't have the same breadth in transports, our tool is strict in depth. For even more depth in checking, we have been experimenting with fuzzing. Fuzzing is the art of finding vulnerabilities with random inputs. The fuzzing tool uses a generated dataset of inputs to test against security keys. Fuzzing external hardware is considered a difficult problem in the scientific community. In our state-of-the-art approach, we guide the random input generation to produce interesting data. For guidance, we leverage OpenSK as a proxy. We provide this input dataset to run against the device under test. All steps are reproducible, and you could even generate your own dataset for testing. So far, we have results of 13 different security keys in our repository and shared our findings with vendors. We double-check our findings with the specification and sometimes reworded to make implementations easier to get right. So please check us out on GitHub, try out the test tool, and contribute your security key results. Before we start the demo, I wanted to give you an overview of the device under test. We will demonstrate the test tool on OpenSK. OpenSK is a free and open source security key firmware. Its idea is similar to Android. You can configure or modify it to your liking, and then deploy it on the hardware of your choice. Or you reuse any parts you like as a reference for your own implementation. OpenSK has no patents, so you can build affordable security keys. It is written in Rust for state-of-the-art memory protection, and it runs on the security-focused embedded operating system TalkOS. Everyone can audit the firmware and build their own hardware. We think that making all steps accessible and reproducible in our projects establishes trust in security keys. Let's see how OpenSK performs under test in a live demo.
The first part of the demonstration is running the test tool on OpenSK. My terminal is showing my clone of the repository. To run the tool, simply type /run.sh. The tool downloads all dependencies, compiles, and then executes. It will prompt you to replug, hit enter, or touch your security key from time to time. Please note that I shortened the run to 20 tests for the purpose of this presentation. One run usually takes a few minutes. Also, building may take longer on your first execution. You can see prints showing immediate results in your console and a summary of all tests after execution finishes. The main output is a JSON file. It is stored in the results folder. Let's check it out. The file contains device capabilities, all information to reproduce the results, and a list of all tests that were executed together with eventual error messages. In this case, OpenSK passed all tests. Let's see another security key for comparison in part 2. So what is the test tool detecting? After exchanging OpenSK, we again type /run.sh. We replug our device, hit enter, and we notice that we're not prompted to touch our security key. Instead, we get warning messages indicating that there should have been a prompt, but the security key did not prompt us for touching. Also, we notice that we can see red error messages indicating that the behavior that the security key is showing is different from what we expect. This includes different responses concerning specific parameters or successful commands when we expect them to fail. Also, sometimes the error codes differ from what the security key should have responded with. In the end, we see a list of all failed tests together with observations that were collected during these tests. We are yet again changing security keys for our last part of the demonstration. This time, we show our new fuzzing command in action. Similar to before, start execution by typing /run_fuzzing.sh. To make findings reproducible, the security key is reset before the fuzzing begins. You will see the tool try out all inputs from our provided datasets. You only have to replug or touch your security key to start testing on a new dataset. Detected crashes are again logged in the results file. We will offer different execution modes, so if you're excited about fuzzing, make sure to check out our documentation on GitHub.
If you like the demonstration, here's a summary of how to contribute your results. After downloading, you can run the tool with a single command. Next, check your results. When you are happy to submit them, create a pull request. As a developer, this is an easy way to promote your awesome work of building a fully functional security key. I'm happy to discuss any issues you are opening or forward questions to the FIDO Alliance. We will make sure that changes in the specification are reflected in the results. At the same time, you can retest new versions of your security key firmware to make progress on a new revision visible. I hope this contribution will be helpful for all of us to make security keys successful. Thank you all for listening.